Hey Geometry, welcome to section 10.3. In this section we're going to be looking at arcs and chords and some relationships between them. So in the same circle or in congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. And so if and only if, remember that's goes both ways. So if their chords are congruent, then the arcs are congruent. If the arcs are congruent, then the chords are congruent. So for example, in this case, if segment FG is congruent to segment HJ, so if those segments are congruent, those are congruent if and only if arc FG is congruent to arc JH, or HJ. I guess we could say it either way. So yeah, we can mark those arcs as congruent. It's a little weird, but we could do something like that if we wanted to. All right, so quick proof as to kind of why this is. So given circle P, arc, kind of it looks a little bit like an arrow. It's kind of hard to get the type to show the arc, but arc QR is congruent to arc ST. So QR is congruent to ST. This is kind of marked backwards. Actually, it should be the other way around. So we're proving that these segments are congruent. QR is congruent to ST. And so if that's all we're given, we can do this proof. So our first thing is we know that if the arcs are congruent, we know the angles are congruent. So I could say angle QPR is congruent to angle SPT, or TPS, whatever way you want to say that. And that's because if arcs are congruent, then the corresponding central angles are congruent. So if arcs are congruent, the corresponding central angles are congruent. So we know that this angle here is congruent to that angle. So that's one thing we could use. The next thing we could use is the fact that this is a circle. So we know that QP is going to be congruent to RP, which is also going to be congruent to PT, which is going to be congruent to PS. So all of those are congruent. So let me write those all down. QP, RP, TP, and SP. They're all congruent. Congruent. Because all radii of a circle are congruent. All radii of a circle are congruent. It's kind of the definition of a circle, right? It's all where the radius is constant. All those points are the same distance away. All right, and then now what we can do is we can actually go back to our, and so we don't technically know this QR is congruent to ST yet. Sorry, that was mislabeled really. We've got congruent triangles. So we could actually say triangle QRP, or QPR, whatever way you want to say it, QRP is congruent to triangle, and then we could say STP. And that's because of side angle side congruence. And then from there, we know that QR would be congruent to ST, so segment QR is congruent to segment ST because CPCTC. We know the corresponding parts of congruent triangles are congruent. And so that kind of proves it. And we could work that thing in reverse as well, go from congruent things here to congruent angles, and then from congruent angles to congruent arcs, and kind of run that proof almost in reverse. So a couple of examples here. We have this embroidery hoop, and segment AB is congruent to CD. We're told that one, and then we're told the measure of angle AB is 60 degrees. Find the measure of angle CD. And so because the segments are congruent, we know arc CD is going to be congruent to, or I guess I'll say the measure of arc CD is congruent to the measure of arc AB, which is 60. And so this would be a 60-degree arc as well. Getting a little trickier with this. Use the figures. So we have circle J and K, and those circles are congruent. So it's not the same circle, but it's congruent circles. And then arc MN is congruent to arc PQ. So we've marked the little congruence there. So because of that, we know that segment MN is going to be congruent to segment PQ, or the chord really. And they want us to find what PQ is. Well, if we know these lengths are 2x plus 1 and 3x minus 7, we can set those equal to each other. 2x plus 1 is equal to 3x minus 7. And then we can subtract 2x from both sides to get just x. And then I'm going to go ahead and add 7 to both sides. And so we get 8 is x. So, careful though, not our answer. They asked us for PQ. So PQ is equal to 3 times 8 minus 7. So we end up getting 24 minus 7, which is 17. And that is the solution to that one. All right, continuing on the next page. If a line segment or ray divides an arc into 2 congruent arcs, then it bisects the arc. So if a diameter or a radius of a circle is perpendicular to a chord, then it bisects the chord, cuts the chord into 2 congruent parts, right? Cuts it in half, and it if the diameter of AB is perpendicular to a chord, then we know that both x in this case, for this example, oh yeah, that's right, bisects the chord and the arc, so these would be congruent as well. I can mark that. So if AB here is perpendicular to this chord, goes through that center, yeah, it's this diameter that goes through that chord, then we know that XZ, segment XZ, would be congruent to segment YZ or ZY. And we know that arc XZ, or XB, I'm sorry, we're going up to B now, arc XB would be congruent to arc YB or BY. You can call it whatever you want with that. And this thing kind of works in reverse. The perpendicular bisector of a chord is a diameter or radius of the circle. So if we know that we're perpendicular and bisecting, then we know that it is going to hit the center of the circle. It's a radius or a diameter. So this one kind of tells us if we are perpendicular and we're a radius or diameter, we bisect. And then the other one saying, well, if we bisect, then it's we know that it's the radius or the diameter, if you go, depending on how far you go across. So in this case, if AB is a perpendicular bisector of chord XY, then AB is the diameter of circle C. All right, so we're going to use this property for a couple of these. In circle S, the measure of arc PQR is 98 degrees. Find the measure of PQ. So, since we know we have a radius, we can see because it goes from the center to the outside of the circle, and it's perpendicular to this chord, we know it's going to cut that in half. So if this full arc here is 98 degrees, then this will be half of that. And so if we do 98 over 2, we'll get 49 degrees for measure of arc PQ. All right, and this next one, use a diameter perpendicular to a chord. In the stained glass window, the diameter GH, and so that's kind of, hard to see here. It goes all the way from top to bottom, G to H, is 30 inches long, and a chord KM, and so this is pretty hard to see here as well. K is here, M is there, is 22 inches long. They want us to find JL, which is right here in the middle. Let me just actually redraw this. I'm going to pause this and redraw this real quick because this is just poor quality. All right, so hopefully it's a little better. It's just trying to label up these points. So G to H, we know that full length is 30. So that means that we know that like this length is 15 and all the radii are 15. So we're actually going to want to use, in the end, they want us to find JL, this distance. So we're going to use the fact that this angle right there is 15. This one over here would be 15 as well. The other thing that you can see here is that this is a right angle. So we do have the rate or the diameter that's perpendicular to the chord, and so we know that it bisects that chord. That chord was KM, which was 22, so we know that this would be 11 and this would be 11. Splits it in half, and so from that we can go Pythagorean theorem here. We could say JL, or I could call it, X or something like that. X squared plus 11 squared is 15 squared. And so if we do that, we're going to get X squared is 121. Sorry, not is, plus 121 is 15 squared, which is 225. And so we can subtract 121 from both sides. We get X squared is 104. And then X is the square root of 104. We could say plus or minus, but we don't need to worry about minus when we're dealing with most geometry here. And so if you wanted to do that as a decimal, the square root of 104, you get that distance of 10.198. So I guess we'll say just 10.2. But that would be the length of JL. So JL is approximately 10.2. All right, so in the same circle or in congruent circles, two chords are congruent if and only if they are equidistant from the center. So this is kind of interesting. So in this case, if LX and LY, LX is congruent to LY, so the distance to the chord, if and only if those chords are the same. So only if and only if FG is congruent to JH. And this works both ways. It's an if and only if. So if your chords are congruent, then you know your distance to the center from that chord is congruent if you go straight perpendicular to it. And then vice versa, if that distance is the same, then those chords have to be the same length. If one of those distances is longer, that's going to mean that chord is shorter or longer, depending on how it lines up. So using an example of that, chords equidistant from the center in this circle A, we know WX and XY are both 22. So that those chords being congruent, they're the same length, so they're equal, so WX is congruent to XY. So I'm making a note of that. That's part of the thought process here. WX is congruent, segment WX is congruent to segment XY. So we know that AB will be equal to AC, so AB equals AC. And so we can set up this problem and solve here. We have 5x is equal to 3x plus 4. A little bit of algebra here. Minus 3x minus 3x. So we get 2x is 4 and x is 2. Let's make sure that's what they're asking for. Oh, of course it was not. We need to plug this back in. And so you could plug it into, they want you to get AB, which you could do 5x. You could theoretically plug it in this as well because AC has to be the same. So, but I'll plug it in. AB is 5 and then x is 2. So AB is 10 in this case.